Hey guys, welcome to OCP 2024. Vince and I are out here on the show floor doing all kinds of fun stuff. Specifically, we've brought out a demo for Solidigm and CoolIT to showcase NVMe power states. We're going to take a look at everything from the tiny baby CDU that we brought out to the big mama jamma behemoth CDU that CoolIT is showing off for OCP. We'll deep dive on those NVMe power states, how they affect performance, and the implications that has on data center design and operations. Hey guys, we're here in the Solidigm booth. We've got our demo up and running. We've got Brandon, a senior vice president from CoolIT here to talk us through this little baby CDU and what its purpose is, why it exists, what it's capable of. Brandon, what would you like to share about it?
Yeah, thanks for the introduction. So what we have here is the Coolit HX2 liquid to air coolant distribution unit. And the reason we have this product is to help our customers test and evaluate liquid cooling technology.
Okay.
What you see here is the coolant distribution unit hooked up to a Dell R760 server, which has our cold plates in it. And we're actually running a test in this server to show its performance relative to air cooling. These units here are designed for 2U, 4-node servers, whether it's in a factory, a lab environment, or a proof of concept like this.
Okay, so what kind of stuff could I hook up to it? How much power will this guy dissipate? Because it's a pretty small package.
It's pretty small. It's designed for up to 2 kilowatts. So it's smaller applications, more for your enterprise or enterprise HPC liquid cooled servers.
Okay, so if I just 2 kilowatts of CPU or GPU or whatever, I'm looking to test the solution. And is it more focused on testing it as a total solution from the cold plates, the server, and the CDU, or is it, would I be using this to go through different servers and test different servers and how they perform?
Either would be fine. The CDU itself was originally designed to help some of our server OEM customers perform burn-ins in their factories.
Okay.
But a lot of our other customers found this to be quite useful. For instance, we're on a trade show floor, and you're able to run a liquid-cooled server with no other infrastructure.
Yeah.
So you don't have to run water to the CDU like you would a liquid-to-liquid CDU. It's very flexible. It can move around with the server, really wherever you want to run that particular system.
I'm envisioning this almost like in a tech's office that is doing service on servers and they want to test something, but they need the liquid loop, right?
Yep. Yeah, it's pretty flexible. We can do different connection kits to connect it up to different server, different type of quick disconnects, different lengths of hose. Usually things we help our customers set up as they're evaluating liquid cooling technology.
Okay, cool. So starting from the small one, maybe I'm just getting into liquid cooling and want to test it, or it's my service unit or something. How large of a system do you guys make?
Yeah, it's definitely, in contrast to this, which is really the absolute smallest coolant distribution unit we sell. If you compare this to actually what we have in our booth, which would be the biggest version of this that we sell, that would go up to 240 kilowatts. So 120 times more capacity than this unit.
Okay.
Very different style of products meant for cloud service providers and co-location data centers that are solving the same problem though. So they're not ready to run liquid all the way to the racks.
Right.
They want to run the latest liquid cooled GPUs, and they need a CDU to make that work. So that same concept that exists in this CDU scales up really nicely to the large row-based CDUs as well.
Okay, so for those playing along at home, how different is something like this from maybe the AIO that I bought to put in my Ryzen gaming rig, or maybe the custom loop that I built? Where's the differences? Where does that kind of, liquid cooling and the enthusiast has been around forever. Yep. I think you guys may have even gotten your start in that space.
That's right.
But how does that transition look from just a single desktop unit to a whole data center type?
Yeah. So you're right. CoolIT's origins are in the desktop all-in-one cooler space, and these days focused on both that and the data center space. But if you look even right here,
they look like rads I have in my computer.
Exactly. They're very similar radiators. So all this is radiators, pumps, and then obviously the control unit and the connection points. So it leverages a lot of the same technology, just packaged a little bit differently and tested to different standards consistent with data center grade products.
Do you make RGB lines for these?
No, maybe one day. Yeah. We don't see the same the need for aesthetic requests on the data center side.
Not as much in this market.
Yeah.
But fundamentally, it's basically the same thing. It's getting the water to the chip and then back out and radiated.
Exactly.
It's just operating on longer distances than inside of a PC case.
Exactly. Yeah. So for our larger form factor row-based liquid-to-air CDUs, we're aiming to support anywhere from 2 to 4 high-density racks. We're talking over 100 kilowatts per rack. To your point, it depends on what are your conditions, what is the heat load per rack, what are the air temperatures, what can the chips handle. Our team helps do all that sizing activity. But our goal with our larger row-based CDUs is to have the largest capacity in the industry and be able to support as many racks as possible. When you look at actually deploying these technologies at scale for AI, you want to deploy fewer CDUs, have fewer points of service, have a lot of redundancy built into the system, not having to do a whole lot of smaller systems joined together. So we aim for big, and we launch a very large capacity product.
All right, well, we saw the little one. Let's go take a look at the big one.
Let's do it.
All right. Your cooler is a little bigger than my cooler over there. So what do we got? What is this? What can you tell me about it?
Yeah, so in contrast to the desktop all-in-one coolers you were talking about, this is a much larger, more data center grade product.
Shinier too.
Shinier too. But it's the same concept. So what we have here is a liquid-to-air coolant distribution unit designed to serve a row of high-density, for example, AI racks. So what you see here, kind of starting from the bottom up, we have our pumps. Those pumps are pushing that fluid through filters. These are redundant, both the pumps and the filters. And they're serviceable, so we actually change, clean filters and replace them as part of like maintenance activities on the system. It's come in 25 micron, 50 micron variants. You see the reservoir in the back. This is different fluid level sensors to know when the system needs to be topped up with fluid. Once the fluid goes through the filters, it then goes up through the pipes you see here, and then out to the IT racks. That collects the heat. There's going to be cold plates in those liquid cooled IT racks, collecting heat from the GPUs, CPUs, whatever's being liquid cooled in those racks. And the hot water comes back into the system to be cooled. And so the way this works, on the other side, which we'll get to the other side, there's fans that are drawing air through this rack and then rejecting heat out of the coil. You can see the coil in the back there. That coil is very much like your car radiator, where your car's likely liquid cooled, and then you have coolant circulating through that hot liquid, and your radiator reject that heat out of your vehicle. It's the same concept. And so just like that small HX2 enables a liquid cooled server to be run on the trade show floor without needing to run a water line to that system. The same concept applies here, where customers who aren't ready to provide facility water into the data center space, but want to run liquid cooled IT, can do that. They can put one of these down next to one or more racks, maybe up to 4 racks in some cases of high density AI systems.
So this is like self-contained, basically like, this is all of the AIO except for the cold plate. Call it the world's biggest AIO, maybe. Does this have the capability of exchanging to, like, if I have a chiller on the roof, can I exchange the heat to that, or we're still relying on rejecting the heat to the air or wherever this is?
The heat is being rejected to air. How that air is handled after that will depend on the site. I can go in within a containment system, different ways of handling that at the data center level.
What is the fluid that's going through here?
So we usually use PG25, so 25% propylene glycol with different bio and fungal growth inhibitors, corrosion inhibitors that make sure that the fluid going through the IT equipment is safe and of extremely high quality.
So it's not pool water that's going to rust my server?
No, absolutely. No, don't run water in that without having done proper validation. So systems can be run with water with the proper validation of the wetted materials that are in here versus the server versus the fluid. Water maintenance and quality is extremely important in liquid cooling, and definitely something that if you're looking to run fluids other than what's on the originally recommended list that we manage, we help customers validate other fluids as well.
Cool. All right, let's take a look at the other side. So we look like we're at the business end as far as where the airflow goes. What are these? What are they rated for? What kind of air do these move?
So we have 2 variants of this product, though the only difference is on the backside of the CDU, where we have, in this case, 4 fans. This is our AHX180, so the unit itself is rated for 180 kilowatts. We also have the AHX240, which has 8 fans, and the main difference is the depth. And so for this one, we limited its depth based on some customer requirements. We have a deeper version of it for that 8 fan that does at 240 kilowatts. And in the we're moving in this variant of the product just over 10,000 CFM, between 10 and 12,000 CFM, and in the larger product, just over 20,000 CFM, probably 22,000. Limiting factors might be airflow. They might have an airflow requirement that they need us to stay under. They might have a noise requirement that they want us to stay under, so we'll keep the fans lower. They might have heat load limitation where we can only connect so many racks to that system. They might be flow limited. So our team at CoolIT is experienced with helping customers size that system. So how many racks can you connect up to it if it has certain GPUs, certain CPUs in it? What's the density of that heat? What's the flow rate needed? These are all calculations that we help our customer understand so they know the performance of the system.
Well, cool. Well, thanks for showing me the big one here.
Yeah.
I'm going to go back and play with the little one and show everybody what we're doing with it.
Awesome. Thanks so much.
Man. So in order to tie all of these concepts together, we put together this really cool demo here in the Solidigm booth that uses the CoolIT liquid cooling solution and a Dell PowerEdge R760 with Xeon Platinum CPUs in it. Let's take a look at how Kevin put all that together in the lab.
Do you want to see if this thing works?
I assumed it worked.
Well, I swapped a lot of parts this morning and I have no idea. Well, it's the first power on since, so I need to confirm it works again.
Kevin and I are working on a demo for OCP. We're doing this in the Solidigm booth, and we've got a Dell PowerEdge R760. We've got this little baby CoolIT CDU. We've got all sorts of data coming out on this platform of liquid versus air. We've got it full of Solidigm storage with a 61.44 terabyte QLC drives. And we're looking at the impact of what liquid cooling means, what modern server builds mean for the data center, what different power states mean. We're really taking a hard look at power with this system.
Yeah, so we took a traditional R760, and this you could buy the server in both air-cooled and DLC setups. We had a different server set up with the cold plates a little bit ago, and moved them over here. Did a lot of component swapping, and actually I could probably pop off the cover.
Might as well.
Yeah.
So we do have a paper on the first R760 we did already, where we took the air-cooled version, got the plates from CoolIT, replaced them, and then ran that again. And what we saw in that paper, we were only focused on CPU in that case. What happens when you add liquid cooling to the server like the R760 is the fan speed goes from 100% under load to like 33% under load, and it's a dramatic power savings. In this case, with this server, that was 200 watts in this 1.2U R760 of savings. So you think about that's just one, but across, I don't know, however many you can fit in a rack, 20, 22, depending on your configuration, it gets to be really powerful, and all of that wattage savings adds up. Now we just have a little CDU, it's over my shoulder here. We'll have to get the B-roll of that so we can show it to you again. And it's effective for about half a rack of gear that we've got set up. This little baby CDU is the one that CoolIT made for us. They constructed this for us.
It's not custom, but it's not a very high volume item. So
it didn't exist. They built it just for this trade show. So this is amazing. So we're going to take this with us. We'll have this server again at the booth at OCP with Solidigm, and we'll be able to show liquid cooling. Oh my gosh, you're going to slide that thing right off the front. So we're going to show the liquid cooling loop and talk about the benefits, what you can see in iDRAC. There's quite a bit there as well.
So the focus for power consumption for OCP is we know that you're going to save power. It's between 190 to 200 watts with the fan power savings. But the impact, the correlation we're going to show is, okay, you have 200 watts to play with. What can you do with that? In certain cases, maybe it means you're going from 12 to 24 SSDs. Maybe it's a thing where you were restricted on your SSD performance by running a lower power state, and now you can go maybe up a state or maybe go unrestricted. So there's a lot of areas where if you're able to save a little bit of power, even in your individual system, you can eke out a little more performance.
All right, in practice, what all of that means is we can run a FIO workload, either a read or a write. We can measure the power draw on our kilowatt meter up here. So in order to demonstrate this, Kevin's put together a couple FIO scripts for us. Let's go ahead and start with the read test here. So this will be a little bit lighter. There's a unofficial term in the industry where people will say reads are free because you don't really have to do anything to read the data out of the cells. You don't have to move stuff, you don't have to erase and then write. It's fairly low power on the consumption. Right now we're sitting at about 843 watts and we're reading across the array. Right now about 94 gigabytes a second. We've seen it go as high as about 100. So that's a pretty good power draw on the reads, but we can get these things to suck down a lot more power. So we can switch it over to a write workload down here and start writing to the drives. We'll see anywhere between 85 to 95 gigabytes per second across the array of 24 drives. But the crazy thing is, this server went from using about 600 watts on idle to almost 1150 watts from the wall in order to do these writes. This is where our power states come into play. So if we can go into our first power restriction mode, power state 1, and go ahead and apply that, we can immediately see that our writes drop down. They do take a significant hit, but our power draw also came down significantly, about 300 watts. We're back at that 850 number, or where we were when we were doing just the reads. And the impressive thing for the SSDs is the read speed in this mode is not affected at all. It actually stays right around 93, 94 gigabytes a second. There's negligible impact to it, and we're actually still saving a few watts on the reads with that first restriction on the power mode. And we can get even more aggressive if we need to on this and go into power mode 2. This is where things start to get interesting. We were able to drop another 50 watts off of our power consumption on our power meter. Our reads started to get affected here. We're down to 77 gigabytes a second, somewhere around a 20% impact, but for that 50 watt savings. Again, the writes will be further affected by this impact, but the point of this isn't to show that you can just slow the SSDs down. It's to start the conversation around when we're talking about removing power from a server or conserving power in the data center, there may be various reasons, whether it's the time of use fluctuations or we need extra power budget in the data center to run some GPU servers. So to tie this all together, we'll bring in our friend Roger from Solidigm, and we'll talk about how these power states tie together across the data center and what they can mean in practice. We're in the Solidigm booth. We've got our demo up and going. We got Roger here. Roger, tell us about who you are. What do you do? I see purple Solidigm, I'm assuming.
First of all, good to be here with you at OCP.
Thanks
Jordan,
for having us.
I'm Roger Carell with Solidigm. I'm the Senior Director of our AI and Leadership Marketing team.
Awesome. That sounds like a pretty tall order.
It's a tall order, but an exciting order. Yeah.
We've gotten the opportunity to do a lot of really cool work this year, though, and some of it's culminated here to the overall demo that we put together for this event. And what we're showing off is the power states that are available in the NVMe spec and how those affect the power consumption of the overall system, right? So.
Yeah.
You had tasked me and the team back in the lab, Kevin and Brian, with setting up something that tells a good story about how you can utilize these. And so we built out a PowerEdge R760 for it. We've got Xeon Platinum Emerald Rapids in there.
Right.
We controlled all our power states. We removed the cooling out of the server with the CoolIT CDU. And then we're cycling through the different power states. So kind of the high level speeds and feeds that we're seeing under full write, unrestricted, about 1100 watts in the box. We can go to power state 1, which is sort of restrictive, and that'll pull down 300 watts off the box. We do take a hit on our write performance, but our reads don't get affected almost negligibly at that first one.
And it's really reads that we care about primarily for
QLCs,
workloads like
position,
artificial intelligence.
Yeah. To not be to not be write intensive, right?
Right.
And then we can go even further and pull another 100 watts off the box on reads and writes by putting them into power mode 2, where we do degrade a little bit of performance, but we're 400 watts under our kind of peak number.
Right.
So you were talking about some interesting things that you can do with that 400 watts, or why it's important to be able to do that.
Okay, so first of all, I think you guys did an outstanding job setting the demo up, because I think it's checking a lot of boxes, if you will, that are kind of key to, I guess, challenges that the industry is facing in continuing to scale out artificial intelligence in an infrastructure efficient way. Everybody's talking about running out of power. AI is a very power hungry workload.
Some of these racks we've seen here this week have been on 120 kilowatts,
It's crazy.
125.
It's crazy. You look at just a couple of years ago, a rack just doing general purpose compute, 12 kilowatts, 15 kilowatts. Yeah, now we're talking 100 plus. It is absolutely crazy. So what the industry is facing is in certain areas, I mean, we are just up against, single or, even a decimal point power available in grids in
Yeah.
in like areas that have high concentration of data centers, Bay Area, Phoenix, Northern Virginia.
Well,
Less than
Microsoft's
2% available.
Turning on a nuclear power
Yeah, and
plant.
then we've got this arms race on. But that's interesting because that's kind of if we maybe look at it in like just simple economic terms, right? That's the supply. Right? Everybody's looking for more supply. Well, what are we doing on the demand side? And that's what you guys are doing here on the demand side is how do we really shrink down the power footprint and to a degree the space footprint as well, because that's one of these infrastructure build out challenges. But primarily the challenge is how do we shrink down the power footprint? And I think you guys are talking about utilizing low power states versus, maybe not peak load times of the day. You're using super high dense, more than sufficient read performance for AI QLC SSDs, which have amazing density, power per watt, power per terabyte capabilities.
It's interesting because even at that first power state, I mean, that's more 100 gigabytes a second across the array on one box. That's more than a lot of line speeds that are in most data centers right now can feed.
Right.
So you're still outrunning the infrastructure.
Yeah. If you've got, if networking is your bottleneck, then take advantage of it.
Yeah, here we go. So I have a throttle to play with on my SSDs now, which is cool because that's unique to the NVMe space, right? You can't throttle a hard drive. It'd be cool. I wonder if the hard drive guys will start letting you run them at like 2,000 RPM.
Yeah, see about that.
Yeah, still be faster with the NVMe though. You touched on it a little bit about power, where there's can be price fluctuations. With renewable energy and stuff coming online everywhere. At night, it can be almost free to run your data center, but extremely expensive during the day. So maybe I can take advantage of throttling for that.
Right.
But what other scenarios would I want to be able to adjust my speeds and feeds on my SSDs?
Yeah, where you've got to your question, where you've got power limitations due to your locality constraints at the edge. Yeah. Power throttling could definitely help out there.
Maybe I have a deployment in like a zoo, for instance.
Right, yes.
They've got a small rack right now, but as they expand, maybe someday some storage provider can put a slider of I need efficiency or I need speed and really be able to show that.
Right.
That kind of brings in some other interesting thought trains too about power limitations in the data center. I can slow down my storage so I can speed up or spin up my AI, right? I can take the chains off those GPU boxes.
Yeah, it's interesting you mentioned that because rightfully so. When you talk about AI data centers, the focus is on the GPU. But I think often overlooked is how can efficient storage help overcome some of these power and space challenges. And we've worked with subject matter experts. We've done research. We've talked in the industry, and we've kind of modeled taking, let's say, a hybrid array, TLC HDD, to all QLC, solving for a certain petabyte. And we're seeing, by the way, huge growth in the amount of network attached storage that goes with a fully populated DGX rack. And like for like, you can get massive improvements in footprint savings, but even more importantly, in some cases up to an 80% reduction in power consumed by the storage subsystem. And so now, all of a sudden, let's say you're dealing with a 50 megawatt data center, and you've got this much physical space, 50 megawatt available power budget, you can scale up more compute due to owing to your storage gains.
Yeah, that's so basically QLC, hard drive displacer.
Yes. Let's say it. Yes.
So
Big and
cool
bold.
stuff. Thanks for letting us come out to the booth here at OCP. It's been a blast setting up this demo and having fun and showing the real-time power.
Yes.
And I think it's gotten folks thinking about other ways to think of NVMe and QLC storage in the data center. Roger, good to see you, man.
All right, good seeing you, Jordan.
Check you around.
All right, take care.
See ya.
Have a good show.
So we learned all about NVMe power states, how that affects our data center design, and what goes into it. We had a lot of fun doing this. Big shout out to Solidigm, Roger, Janice for having us out, and thanks again to Vince for running the camera. Everybody say hi, Vince, in the comments. Make sure you like, subscribe. We've got a link in the description to the Discord where you can come hang out and ask us any questions, and we've got a link in the description to our full paper and our write-up. We'll see you around.